Okay, in this video we're going to take a look at determining the nature of functions. So just as a wee review, so far we've taken a look at several types of functions. There's linear functions and some examples of those. We had quadratic functions, and again some real world examples of these: the power from the wind versus blade length, stopping distance versus speed. We had cubic functions, volumes, power from the wind versus wind speed, and power used versus speed for pumps and fans. And then we had reciprocal functions: Boyle's law, speed versus time, torque and speed for a motor. So first things, guys, especially those of you doing exams and stuff, you need to be familiar with, first of all, the functions, their graphs, their equations, and then real world examples of these functions. So this page would give you a good kind of summary of real world examples of the functions we've been examining so far. Now, the topic we're about to do, determining the nature of these, I would consider fairly important. So if you're one of those people who's decided to study maths at the last minute, you could be watching the right video. Now, the concept, what we're really looking at here is when someone does an experiment, you plot your input and your output, but often you can get kind of a graph, and I'll just do a little example here, which might say look like this. So here's our inputs, I'll just call them X to keep it nice and general, and here's our output, Y. Is we could say, well, once we start plotting our data, it starts to look like this. And we could kind of make a guess. We could say, well, it looks maybe like a quadratic curve. But the thing is, unfortunately, you can't make that assumption, because this curve could be quadratic and we can't see the left hand side of it, but it could also be a cubic function, which would look like this, or it could actually be an exponential growth function. So they could all produce the same looking curve, but we can't be sure what the nature of this function is, and that's what really we're looking at here, is how do we determine the nature? Is it quadratic? Is it cubic? Is it reciprocal? So that's what we're aiming towards. And how we go about it is by testing the function. We apply the suspected inputs against the outputs, and if we get a straight line, we're there. So I'll just explain this a little bit better on the next slide. So often you kind of suspect, so in the exam I might talk to you about torque and speed of a motor, and from the list I had on the first page of this video, you should then suspect a reciprocal relationship. Or if I was talking about the volume of a shape, you should suspect cubic. Area, you should suspect quadratic. So I don't know if you can hear the dog is snoring again, but so to test if this relationship is valid, so to test whether it's quadratic or cubic or reciprocal, we draw a new graph with the inputs and the outputs arranged. So just to kind of explain, say if we're told someone is measuring an area, well then area is a quadratic, so we suspect this. We'll be given a table of data for X and Y. This will be part of the question. Here's your Y value. Now, what we do is we'll actually say, right, because we suspect it's X squared, we'll draw a new line on the table and we'll evaluate X squared. And then, so for each X value, say if X is 2, X squared is 4, X is 4, X squared is 16, etc. And we'll have Y values here already kind of recorded from the experiment, something like that. So now, what we do is instead of plotting X versus Y, we now plot X squared versus Y. And if you end up with a straight line, which would usually be aimed towards the origin, if once you get this straight line, you've now verified that y is proportional to x squared. And if we wanted to get the exact equation, we could get the slope of that straight line, and now we could say y is equal to m by x squared. So it's a very useful concept, because what it allows us to do is turn experimental data into mathematical equations, and then from there we can start to predict how the function will act into the future. So just say, for example, if we suspect the relationship is quadratic, then plot y versus x squared. As I was saying, guys, you'll be given x and y, you'll be given a table with x and y as part of the question. If you suspect it's a cubic relationship, then plot y versus x cubed. Or if we suspect it's a reciprocal relationship, then plot y versus 1 over x. And then, as I was saying, if you end up with a straight line, a linear relationship, this verifies that the relationship is governed by the function we suspected. And as I was saying, we can actually determine the exact equation by getting the slope. So we'll start by looking at a reciprocal relationship. So determining if a function is inversely proportional. So how do we know? This is just a quick rehash. So first of all, how do we know if data is inversely proportional? Well, first of all, we could draw a graph. And a reciprocal relationship, hopefully, as you know, would produce a graph which looks like that, which, again, you could suspect that's reciprocal. Here's our x and our y. When we plot x versus y, we get this graph. But this graph could actually be an exponential decay curve, which often produces the same type of curve. So unfortunately, drawing a graph is not conclusive. But if we plot y, instead of having x on this axis, we put 1 over x, and we plot y, and we end up with a straight line plot, this conclusively verifies that y is proportional to 1 over x. And that's what we're trying to do initially, is just sort that. So we'll take a look at an example. So a student is measuring volume of a gas at varying pressures using the apparatus shown below. So this is fairly standard kind of physics experiment to explore Boyle's law. So now Boyle's law, from our list at the start of the lecture, we should be suspecting it's a reciprocal relationship. So straight away, guys, from the information here, we suspect y is proportional to 1 over x. We suspect this reciprocal relationship. So here's the data gathered in the experiment. So we've got P and we've got V. So like putting in our values, now pressure is our input, that's been changed. We changed the pressure and we measured the volume. So volume is our output, pressure is our input. So now we're suspecting that volume is proportional to 1 over P. So the student suspects the data exhibits an inverse relationship, another word for reciprocal relationship. How would she verify if this relationship exists? So we take a wee look at, this is your solution now to this. So this is how the problem could appear on the exam. Now we're given this data here. What we do is we create a new line in the table. So because we suspect volume is proportional to 1 over P, we want to calculate this value for each value of P. So we have P here, but what we actually want is 1 over p. So it's going to be 1 over 2, 1 over 8, 1 over 16, 1 over 24, 1 over 32, 1 over 40. That's where we're going to start computing. So there's our 1 over 2, 1 over 8, 1 over 16, 1 over 24, 1 over 32, and 1 over 40. So now, we've determined those values, and now we plot these new values, 1 over p. Again guys, 1 over p is our input. That's your horizontal axis. And then the volume is our output. And if we get a straight line, that verifies that our inverse relationship exists. So we take a look now. You guys would be drawing the graph and stuff, and we'd be plotting, as I was saying, input. So 1 over p is along the x-axis, and v is on our y-axis. So this is our graph, and we can see it is a very nice straight line, and it is heading towards 0, 0. It'll never actually go towards 0, 0 because we would never really record this data. So now guys, we've verified, because we've got a straight line, we've verified that v is proportional to 1 over p. Now I'm not going to do it because I just don't have the time, but we could get the slope of this line, m, and now we could say v is equal to m times 1 over p, that's capital P, so it's m over p, and this m guys is related to your Boyle's law. PV is equal to nRT. So these two equations would be related then, but I don't want to head down that road. All we're doing at the moment is determining the nature of the function, and now what we've done is we've determined that this data is of a reciprocal nature, and now we can go on. If we need to, we can calculate the equation. So now the same method can be applied to quadratic functions. So we look at a quadratic example now. Just giving a wee overview first, if we plotted the area versus its radius, we'd produce this curve. Again, notice in the real world, guys, you never really get the negative side of things. You only get kind of half the quadratic curve. But it's not enough to take a look at the curve and say that looks quadratic. That's not scientific enough. We have to verify its nature. So because we suspect area is proportional to r squared, we're going to plot a versus r squared. And when we do that, we get our straight line passing through the origin. So this verifies then that a is proportional to r squared. If we get the slope of this graph, it's actually pi. So now the exact relationship is a is equal to pi r squared, which is the area of a circle. So we'll take a wee look. So this is kind of worded a little bit vaguely, but the key word there is area, and its primary dimension, guys, is just another posh word for length or radius or height or whatever. It's just been more vague. Could be length, radius, height. So it's just giving us a kind of vague outline of what's going on. It could be any of these, but it's going to be measured in meters or whatever, or centimeters. So these are our inputs. Length. Our output is the area, that's what we're measuring. And when we plot them, we get this curve shown in the bottom right. Now, Just some of the questions. Determine the nature of the function by drawing a suitable graph. So whatever you do, guys, in the exam, don't produce this exact graph again. You're already given it. You're not going to get any marks for producing the same information. So we're going to draw our A versus L squared graph. That's the first step. Then write an exact function relating surface area to dimension. What that means is we need to get the slope of that straight line graph we'll get, and then suggest a common shape which exhibits this relationship. It's usually fairly straightforward, so we'll take a look at that as it rolls around. So as area is a quadratic relationship, we suspect area is proportional to length squared. We add a new add a new line to the table of length squared. And now we're squaring each of these values. This squared will give us 0.81, etc. Square 1.05, square 1.2, square 1.3.5, square 1.5. And now draw the graph of area versus length squared. Again, guys, length squared is your input. That goes on the x-axis. Don't ever mix those up or you'll be heavily penalized. And when we take a look at this graph, when it's drawn, you guys be using graph paper and stuff like that, taking a bit of time over it. We see we've got our straight line, so we can now say, well, area is proportional to length squared. The straight line verifies that this relationship exists. That's a squared there. So now what we want to do is determine the exact relationship. A is equal to what? L squared. And to do that, we need to get the slope. So because all the points are nicely on the line, I'm just going to pick 2 points from the table. x1, y1. x2, y2. And then, guys, we get the slope using our slope formula, y2 minus y1 over x2 minus x1. Calculate this out and we get m is 3.14, which is very close to the value for pi. So we can assume the value is pi. So now that's our relationship. Pi L squared, most commonly known as pi r squared. So what we're looking at here is most likely the area of a circle has been examined as the radius changes. So now we'll push on, do one more example looking at cubic functions. This time we're going to be looking at volume. Now again, guys, any of our cubic relationships discussed at the start of the lecture, we could be looking at power from the wind versus wind speed, because that's a cubic relationship. Or power drawn by a motor versus the speed of the drill. That's a cubic relationship as well. So here's a relationship. We're plotting volume versus radius, and we can see we get this curve. Now again, guys, you could be easily mistaken into thinking that that's the right hand side of a quadratic. So it's very hard to kind of just assume by looking at a curve what its nature is, especially when half of it's hidden from us as well. As is the case, we can never have negative radius. It doesn't exist. So we suspect it's volume versus r cubed, so we plot volume versus r cubed, and this gives us our nice straight line. And now we've verified that v is proportional to r cubed, and if we got the slope would work out to be 4 over 3 pi, and then we'd know the relationship was that v is equal to 4 over 3 pi r cubed, which verifies we are looking at the volume of a sphere. So again, as before, we'll just take a look at an example worked out in full. So the amount of air in a vessel, again guys, the wording is quite vague. So hopefully the word volume would be suggested there. Here's our recorded data and associated plot. And same questions as in the previous example. The main thing here though guys is that we suspect the relationship is cubic. V is proportional to L cubed. So we add a new line to our table, length cubed, and we cube each of these values. Now this causes us a little bit of a problem, especially when we're looking at 22 cubed. We can see we're up into the 10,000s. So drawing the graph of this isn't now, it's certainly possible, but it's going to be very hard to get any level of accuracy when we need this axis here to go up as far as nearly 11,000 on a normal size graph. So there is an alternative, and I'll just do the maths of it first. So we suspect V is proportional to L cubed. Now the proportional sign guys acts the exact same as an equal sign. So what I'm actually going to do is cube root both sides. And now I'll have the cube root of V is proportional to L, because when I cube root this side, that kills the cubed. And now guys, we can actually test this relationship. So rather than getting L cubed, which is resulting in these very large values, which can be a bit tricky to plot, we can just change things around, because if we get a straight line for this relationship, then if this relationship is true, by the nature of maths, this relationship must also be true. So it's just a little get around, and it'll work for either of the previous examples as well. We're going to investigate the cube root of volume versus length. So now I'm actually writing a different new line where I get the cube root of the volumes. So I'm simply into the calculator guys is getting the cube root of each of these values. Cube root now, not the square root, that's a cube. So that's what we're doing there, and now we can actually see there's quite an obvious relationship between length and cube root of volume, and that's what we're going to plot. And we see we get a straight line, and again, if we continued it on, it would be heading directly towards the origin, which proves proportionality. So we can say the cube root of V is proportional to L, and if we cube both sides, we get V is proportional to L cubed. Now just with this graph guys, I'm not going to do that in full, but if you did get the slope, you'd end up with a slope of 1, and that would say then that V is equal to L cubed, and this would suggest what we're actually looking at is a cube of side L. That's what we're really looking at there. So that guys kind of finishes off this technique, really determining the nature of functions. You apply your suspected relationship, draw a new graph. If you end up with a straight line, you've verified proportionality. So we leave it there, and thanks very much for listening.